Why do we need multi-output Gaussian processes? Why we would like to have them? So this is a classical example in sensor networks. So this one is a sketch of the south coast of England. And there are some base stations around the coast. And these base stations have sensors networks. And these sensors are measuring different environmental variables, like temperature or high tide or air pressure. And typically from sensor networks, what happens is that this information is communicated to a central base, let's say. But what happens is due to different communication problems or because of the sensors are faulty, what happens is that we usually miss some data. So since we know that there is a common natural phenomenon that is happening around the south coast, we could wonder if we could learn what we learn from these sensor networks, for which one we do have the whole data, can be somehow be used to try to input data into this signal that has missing values. So we want to learn from this data and transfer that knowledge to input the values of this sensor. So this is one first motivation for multi-output Gaussian process, and is related to the idea of transfer learning between different outputs of processes. This is a second motivating example. So this is a sketch of the Swiss Jura. And a long time ago, there was mining activity around this area. And today we have like a screenshots of the concentration of different pollutant metals. So we have access to the concentration of some of the pollutant metals, like copper and lead, in blue and red here. And we also have access to the pH level at the same, mostly all the input locations. So the idea is that pH level is usually very cheap to measure, but the concentration of the metals probably is more expensive to measure. And what we want to do is to sort of use the pH level as a proxy to try to predict the value of the metal concentrations for those input locations where we don't have access to it. So for example, in this input point A, we have access to copper and pH, but we don't have the concentration of lead. Something similar happens in the point B, where we don't have access to the measurement of copper. So is there a way in which we can sort of learn a model for those input locations for which we have access to the values of those three variables, and use that model to try to predict the concentration for those more expensive variables for which we don't have access? Is that clear? All right. How do we define dependencies between processes? So I'm just going to review what you saw yesterday, talking about single output Gaussian processes. We know that a Gaussian process already is a random process, such that if I take a finite number of random variables associated to that process, then those random variables are going to be multivariate Gaussian distributed. This is another sample from this Gaussian process, another example. So if we define some input locations, then for those input locations, we are looking at some random variables. And then what we say in Gaussian process is that if we group those random variables defined for those input locations, then this random vector here is going to be Gaussian distributed in this way. So as Richard said, usually in machine learning, we use a mean function of 0. And then the covariance matrix for this vector is going to be computed from the kernel function that we use for our Gaussian process. So I'm going to use bold F to refer to these random vectors that have the random variables associated to the GP, and I'm going to use this bold K to refer to these kernel matrices that contain the evaluations of the kernel function. And then, since this is our model for the Gaussian, and then we know all these nice properties of the Gaussian process now, that marginals and conditional are also Gaussian, I can compute a predictive distribution given some particular data that I have in mind, that I have with me. So for a new input location, X star, then I can compute this predictive distribution, which is again a Gaussian distribution with particular mean and variance. Right, sometimes we don't have access to the samples directly. What we do, for example, in regression is that we assume that the observations are connected to this underlying process through an observation model. So we say, for example, what we observe is really this underlying process plus some noise, which in the typical regression case is Gaussian noise, with a variance sigma squared, let's say. Then again, I have my data, and this is my whole Gaussian, multivariate Gaussian for this random vector now, that now includes the covariance of the Gaussian noise associated to this additional process. Okay, so again, we can compute the predicted distribution if we compute this density using the properties of the Gaussian, multivariate Gaussian distribution. What happens when we have several processes? And this is where things start to become interesting. So, not far time ago, people usually in machine learning would say, well, if I have to model different processes, what I do is that I'm going to assume that those processes are independent, and then I use a GP for each of the processes. Yeah. So this is a first scenario where we have two random processes. Each of them has a Gaussian process assumption with covariance K1 for process F1 and K2 for process 2. Then here are some samples from this multivariate Gaussian process. I can define some input locations and the value of the process on those input locations, the same for the second process. And what I say is that if I do this, then my vector value function for F1 is a Gaussian distribution with covariance matrix K1, and the same happens for the second process. The vector value with these entries has a Gaussian distribution with kernel matrix K2. Right? So what I do is that I create now a larger vector F that is going to have vector F1 and F2 stack. And then since I am assuming that these two processes are independent, the blocks outside the main diagonal are going to be 0 because the dependency between them is just 0. Right? I could also have noisy observations for these two processes, like here, and then also have an observation model for each of them. And then I would just add this additional covariance function for each of the vectors. And then I will get this representation for, again, the stack vector of the noisy random vectors. Again, what we see here is that I'm assuming the independence between them. Okay, so really what I would like to do, and according to the motivations that we saw before, is a way in which I could exploit dependencies between the processes. So the question here is, how do we define these terms that are outside of this big kernel matrix that now you have? So yesterday, Nicola was talking about the conditions for a kernel function to lead to a kernel matrix. And so he was saying first that that kernel function has to be positive semi-definite and has to lead to a kernel that is symmetric. So we basically need to do the same things in the case of the multi-output Gaussian process. So if we're going to define a way to compute these kernel matrices, we first need to define a covariance function such that when I compute the elements of these parts of the matrix, then the whole matrix is going to be positive semi-definite and is going to be symmetric. And that's the basic challenge that we have. How do we come up with ideas or models or ways in which I can compute these cross covariances between these two processes, and then the whole covariance matrix that I get is going to be positive semi-definite. Right? Okay. So before going into that, I just want to make these definitions for the different configurations that we could have in the input data. So these definitions actually come from geostatistics. They are not used really in machine learning. So I use this black dot to refer to the inputs of the process F1, and this square to refer to the inputs of the second process. So we said that the input configuration is isotopic if the sample size for both processes share the same input points, as you see there. So when I write that, basically what I'm saying is that the data sets that I have the same input points, and then the processes are evaluated at the same input points. Not only that, but I have the same amount of observations per process, so capital N and capital N. This is the isotopic data case. And the heterotopic data case allows me to have different sample size for the two processes. So you see that there are still some of the sites that are shared, but I have more observations for second process, let's say, than for the first process, and then have N2, so the number of points here could be different to the number of observations here. That's the heterotopic case. Usually we don't talk about this with these terms in machine learning, yeah? All right. So we are going to start building these cross-covariance functions. So we are going to start with a very simple model, and then we are going to make it more complex until we get to the convolution approach. So we're going to talk about the intrinsic regionalization model first, or the ICM model. So the first, so I guess the easiest way to understand this way to build these cross-covariances is looking at the generative process for this way of constructing the multiple output Gaussian process. So consider first that we have two outputs, F1 and F2, and X lives in RP. And we're going to assume the following generative model for the outputs. So the first thing that we do is that we sample from a Gaussian process UX that we're going to assume has a zero mean function and a kernel function kx prime. We sample from that process and we obtain a sample which is u superscript 1x. We take that sample and we transform that sample, scaling it by this coefficient, a sub 1 super 1, subscript 1 superscript 1, to represent one of the outputs, f1x. And we use a different coefficient, a subscript 2 superscript 1, to scale the sample from u to represent f2. So it's a very simple model. Here it's just a representation of the idea. So we sample from u and we obtain u superscript 1x, and then we scale that sample to obtain a representation for f1 and a representation for f2. We repeat another sample like this one, and then we get representations for f1 and f2. Something to notice here immediately is that both outputs have the same shape, and this is obvious because they are sharing the same underlying sample. Yeah? The only difference there, as you can notice, is if A1, 1 and A2, 1 are different, then we're going to have different scales in the outputs. Yeah? Okay. Right, so imagine that we fix x, so we can group the two functions in a vector. Yeah, so the vector fx, we're going to refer to it as a vector value function. In fact, it's a random vector value function. Because the inputs are given by individual outputs, individual functions, f1 and f2. And what we're going to do is to compute the covariance for that vector. Yeah? So we apply the definition of the covariance between two random variables or two random vectors in this case. Remember that the definition says that if I want to compute the covariance of a vector, then it's going to be the expected value of the vector times the same vector transpose evaluated at x prime minus the expected value of the vector times the expected value of the vector evaluated at x prime transpose. Yeah, so here we are doing, what kind of product is this? An outer product, yeah? So we have a column vector that is multiplying a row vector after transpose, yeah? So we get a matrix here, yeah? Right, so let's look at this term first, and then we look at this term. So we just replace the vector for its components, and the same here, and we do this outer product. So we get f1 times f1 x prime, f1x, f2 x prime, f2x, f1 x prime, so forth. And then we apply the expected value over the elements of the matrix, and we get this expression that you see here. And then what we have to do is to see what are these terms. What is the expected value of these terms? Right, so we can compute those expected values as you see there. So it's very easy to do because f1 is just a1, 1, u1. And then just the value for f1 is this, f1 x prime is the same, but I replace x for x prime. So at the end I get for the first term this coefficient a1 subscript and superscript 1 square, and the expected value of u1x. So just for you to remember, the subscript in these a's that appear here refer to the output. So a subscript 1 refers to output 1, and the superscript refers to the sample of this Gaussian process, this latent Gaussian process u. We do the same for all of them, yeah? And then we can group them, put them back in the expression, and then we can notice that the expected value that we end up with is just the expected value of the latent process, the sample of the latent process, u1. So I can factorize it, I get this expression, and I get this matrix here. Yeah? Okay. Then this is the first part of the covariance. I then get the expected value of the vector, and then that expected value is just we replace there, and we get this expression. So it's just the this vector that contains these scales that we had before times the expected value of the latent process. So we put all those things together, and we get this expression, this first expression that you see here. I'm going to define just a vector to group all these variables A. So I'm just going to call it bold A here. And then what happens is that I can factorize this matrix, because basically it's the same matrix, and then I get this outer product of the volt A times the covariance of the latent process. Yeah? So the final expression that I get is that the covariance of this vector value function is going to be an outer product times the covariance function of the latent process. Is that clear? Yeah? All right. So we can define a matrix for this outer product. We call it usually V. So, and that leads to, again, this expression here, where I have now this matrix defined in terms of B instead of the outer product A. So if I want to build a multi-output Gaussian process with particular covariance, I could either define A, or I could try to estimate directly B. Right? Okay. So notice that B has rank 1, yeah, because it's just an outer product. And that's the easiest way in which we can build our first model for multiple output Gaussian processes. Okay? So we could do more complex, yeah? Why to stop just one sample? Okay, so why do we don't like the model before? Because as I said, when we look at the outputs, they just have the same shape. The only difference probably is in the scale. So we want to have a more complex model to represent the outputs. And the generative model for that is as follows. So now we're going to sample twice from this latent process, ux, with covariance kx prime. And then we obtain two samples, u superscript 1 and u superscript 2. And what we're going to do is to make a linear combination of those two samples and use that linear combination to represent the output 1 and another different linear combination to represent the output 2. Yeah, so the only level of complexity here is that I added two terms, one for each output. Right? So something that is important to notice is that these two samples that we get from the latent process are independent, although they share the same covariance. Yeah? So probably you're familiar with the IIG assumption that you use in statistics. Yeah? So you say, oh, random variable is sampled independently and identically. So you can think of this as the same way. So I'm using this process ux to sample independently two random processes. Yeah, but they share the same probability density. Okay. Right. So again, I have this sample for U superscript 1 and this sample for U superscript 2. So I sample them independently and then I linearly combine them to get a representation for the output, like the one you see here. This is another sample, and this is a different representation. So you can see now that there is a difference between the two because we broke that symmetry by adding a new sample from the Leighton process. Yeah? Okay. So we can express that vector value function as you see in that equation there. So we say we have a vector A superscript 1 that has the first elements A subscript 1 superscript 1 and A subscript 2 superscript 1. And then that multiplied by the random sample U1 plus the vector A2 times the random sample U2. Then I can compute the covariance as we did before. So I'm just doing it here more quickly. So you just compute the covariance, and then since these two processes are independent, I can just compute the covariance for the first term plus the covariance of the second term, and I get this expression here that reduces to this expression and reduces to this expression. But remember that the two covariances are the same because the samples share the same covariance, so I can factorize k and I get this expression. So now we have V again, but before V was just the outer product of one vector. Now V is the sum of two outer products. That means that the rank of V is 2. Yeah? And then again, I can express the covariance between F and Fx prime using this matrix B instead of these vectors A in this way. So it's just this matrix V times K. So something that is important to notice, maybe I didn't make emphasis on that before, is that this matrix is going to be symmetric, yeah? Because we're doing these outer products. Yeah? Okay. Good. So what happens when we have observed data? So imagine that these are two outputs, and then in particular input points. This is the isotopic case in which I'm assuming that the input points are the same. I define these random variables for the first process and the random variables for the second process. Then I join them into this huge vector. So I have a random vector for the first process and the random vector for the second process. And now the covariance is going to be given by this expression that you see here. So instead of having the zeros that we had before, now we have included some terms into the diagonal, the terms of the diagonal, such that the whole kernel matrix is positive semi-definite. So the elements of this matrix K are computed using the kernel of the Leighton process. And there is a way in which I can summarize these expressions is by using something called the Kronecker product between two matrices. So the Kronecker product between matrix C that has these dimensions with this matrix G dimensions G1 times G2, where C has this form that you see here, is defined in the following way. So I take each of the elements of the matrix C, and I multiply that element times the whole matrix G. And then I form my huge matrix as the Kronecker product of the two of them. Is that clear? So what are the dimensions of this matrix?
C1, G1 by C2, G2, right?
So, say again, sorry?
C1, G1 by C2, G2.
Oh, yeah, that's right, yeah. So we have how many C's in the rows? We have C1. And how many rows for G? We have G1. So how many rows do we have? We have C1 times G1, yeah? Okay, thank you. Good. Okay, so this is the same representation that we had before. And then we can just generalize this, yeah? So instead of just having two, we will have, in general, D outputs, capital D outputs, and then we have this equation, or this representation for the output FD. And then the U superscript IX are random samples from a Gaussian process with covariance KX prime. And then again, I can compute the covariance function that now has this form, A transpose, where A has this amount of columns, where R is the number of columns in this A. Yeah, and basically what we are saying is that B is constructed by adding R outer products of these vectors, so the rank of B is equal to R. Yeah.
Could you say again how can we estimate the A like more?
I'm going to talk about that later. Yeah? Yeah. Okay. Something important about this model, people sometimes don't know this or they forget about it. So for the ICM, we have this phenomenon that happens when you want to make prediction and you have noisy free data. So if you consider that your outputs are noisy free, the prediction using the ICM under the isotopic data case is equivalent to doing independent prediction for each of the outputs. And that phenomenon is known as autocorrigibility. So I'm going to talk about later when we see the equations of prediction and how is that a process that is supposed to account for dependencies ends up just doing independent prediction for each of the outputs. Right. This is our second model. It's called the semi-parametric Leighton factor. Sorry, yeah. Yes, yeah, I will see that later. Yeah, yeah. You could do that, yeah. Thank you. Okay. Okay, so the second model is the semi-parametric Leighton factor model. We're going to see what is the generative model for this case. So first, remember that in the previous model, which is called the ICM, we used in the general case R samples that we call U subscript I from UX. Yeah, so we sample R times from this Leighton process. And this Leighton process has, we said, it had covariance KX prime. Now, the semi-parametric Leighton factor model uses capital Q samples. So I'm going just to change R for capital Q. You will see the reason in a moment. So capital Q samples from U sub Q processes. And each of the process is going to be a Gaussian process with its same, with its particular, covariance function. So now, instead of sampling from the same process, I am sampling from capital Q different processes. Is that clear? So the two models are the same when capital Q is equal to 1 and R is equal to 1. So again, consider that we have two outputs, F1 and F2, and we are going to assume that Q is equal to 2. And then this is our generative model for the outputs. So first we get a sample from a Gaussian process with covariance K1, X prime, and we obtain U1. Then we sample from a different Gaussian process, not from the same. If we sample from the same, we are talking about the ICM. This is a different Gaussian process with a different covariance function, K2X prime, and we obtain a second sample, U sub 2, subscript 2X. And now to model F1 and F2, what I do is just a linear combination of those two samples in a similar way to what we did before. So this is a linear combination of U1 and U2 with these two coefficients for F1 and these two coefficients for F2. Right? So let us compute the covariance for these expressions. Well, for that, some samples from this model. So first, this is a sample from a Gaussian process, which I try to do a long length scale in this interval. And then this is another Gaussian process with a short length scale. And then when I add them, I get this representation for the outputs. So they look quite different to the ones that we had before. Yeah? It's another sample. You can look at the different Leighton functions that we have and how different the outputs are with this linear combination. So let us compute now the covariance. So again, I can represent the vector value in this way, as you see here. So a vector A1. Look now that the script that I use, the index that I use is a subscript. In the case before, it was a superscript. Yeah? And then when I compute the covariance, I get, again, these two processes are different, they are independent. So I get a first term that is the outer product of this vector A1 times the covariance for the first process plus the outer product of the vector A2 times the covariance process, so the covariance function for the second process. So what we had before is that those two covariances were equal, so I could just factorize it, but here I can't do it because the covariances are different. Yeah? Is that clear? Okay. And then I can define again two matrices of rank 1 as these outer products, and then write then the covariance of F as the sum of these two covariance functions. Okay, so now we have some observed data. Again, we define some input values, and for those input values, then we have these random variables for the process 1 and the process 2, and then we want to jointly model the stack vector for F1 and F2, and this is the way in which we would model the covariance for the whole vector, which is just the sum of the Kronecker products between V1 and K1 and V2, K2. The elements of the matrix K1 are computed using the covariance of the first process, and the elements of the matrix K2 are computed using the covariance for the second process. And I can just do the general case, yeah? So now Q is greater than 2, and then I express my outputs as a linear combination of capital Q processes with samples that are being transformed linearly. So these U sub Q are Gaussian processes with covariance functions KQ, and then I can represent this in a, say, vectorial way. I can group the vectors A into this matrix AQ, which actually is just a column vector, and then again express the covariance for this random vector value function as the sum of from K1 to capital Q of BQ times the covariance for each of the processes. So something that we have to be careful here is that these covariances, this matrix is V sub Q at rank 1, all of them. Yeah? Any questions?
What's the bigger picture?
We are getting there.
Is it possible you can go back and give a synopsis of the bigger picture? Because I don't know if I'm the only one, but I've really lost how the things relate.
Yeah, they are going to connect in the next model. So the way I'm introducing these models is because they have been proposed as different models in the literature. Yeah? Yeah? Okay. So now we get to the big picture. And the big picture is called the linear model of co-regionalization. Yeah? So in the linear model of co-regionalization, I mix the two ways in which I'm combining the processes. So basically what I say is that I have a set of functions, a capital D, and each of the functions is going to be a double sum of some coefficients AD, comma Q, superscript I, times these random samples U, superscript Q, superscript I of X. This is the big picture. That's why it was better to look at slowly. Yeah? So what we are doing, what are we saying here? So when capital Q was equal to 1, what was that model? The ICM. Yeah? And where R sub Q was equal to 1, which model was that one? Say again, sorry? The semi-parametric Leighton factor model. Very good. Yeah? So I'm just combining the two of them, and I'm just calling this the linear model regionalization to build a covariance function. Yeah, right. So the property of these processes, these Gaussian processes, is that the covariance, if I just compute the covariance between two of those processes for, let's say, Q and Q prime different and I different, then it's going to be 0. The only way in which it's different from 0 is if these indexes I and Q are the same, and I get the covariance for the process U sub Q. How can we understand that equation? So this is a way to understand the equation. So again, we have the expression for the outputs there. We can think about this equation as, imagine that we have capital Q groups of samples, yeah? And for each group of samples, so this is group 1, group 2, group Q, and for each of the groups, we have R sub Q samples. And those R sub Q samples are obtained from the same random process, from the same Gaussian process with covariance function K1, K2, K capital Q. Yeah? So this is the way in which we could understand our equation there. Is that clear? Okay, good. Right, so this is the linear model coregionalization. So let's look at a particular case with two outputs. So we have another way to understand the linear model of coregionalization is just to think about it as the sum of capital Q ICM models. Yeah? So each of these groups of samples here correspond to an ICM model. Yeah? Okay. So we have two outputs. We have two different random processes, and then for each of those random processes, we have two samples. And according to LMC, this would be the first ICM for Q equals 1, let's say. And this process will have the same covariance function. And this would be the second ICM, where this process U2 has a different covariance function, but the samples are obtained independently. So these are samples that we can get from this LMC model, as you see here. And then we can just compute the covariance for this model, and the covariance for the model is going to have this expression again, very similar to the one that we had before. But in the semi-parametric Leighton factor model, this matrix is AQ, were only just a column vector, and now there are matrices with R sub Q columns. Yeah? So the rank of this matrix, each of these matrices is RQ, and these matrices are usually known as co-regionalization matrices. Yeah? They don't have always, they don't need to have the same rank. So I could have an ICM model with rank 2, let's say, and then another ICM model with rank 3 or 4. Yeah? Okay. Once again, if I have some finite number of random variables from this process, I can stack them, and this could be the covariance for the join process, which is the sum of these Kronecker products, where the elements of this matrix KQ are just computed from this covariance associated to each Leighton process. Right. Okay. So the linear model coregionalization, which is the most general one, has been known in geostatistics since the 70s. The ICM model was introduced in machine learning in the NIPS paper in 2008, but it was, as you saw, a particular case of the linear model of coregionalization. The semi-parametric Leighton factor model was introduced also in machine learning in 2005, but yet again is a particular case of the linear model of coregionalization. Yeah? Okay. So this is the sort of the first big family of ways to build cross-covariance functions. Now we're going to talk about a different family in which we construct these cross-covariance functions. And that family comes with the name of process convolutions. Okay. So again, we have a set of these functions, and we are going to represent each of the functions as a convolution integral between a function GD that we're going to refer to as a smoothing kernel with a latent process UC. So sometimes this operation is referred to as a moving average function, because basically what I'm saying is that if I sample from this process UC, I haven't said how that process is, but let's say I have a sample of UC. Yeah, what I'm doing is using this smoothing kernel and moving this smoothing kernel around the sample, and then for each of the times I move, for each of the points in which I move this smoothing kernel, then I just compute the integral between this portion of the underlying signal and the smoothing kernel. Then I move the smoothing kernel and I compute again this integral, and I keep moving it like that. So basically what I'm doing is that if this sample is very rough, by doing this integration, I'm sort of smoothing that sample. Yeah? Right. So for this integral to exist, this smoothing kernel has to be a continuous function, and it needs to have compact support and be square integrable. What does it mean, square integrable? That if I do the integral in the whole space of this function square, then it has to be finite. Yeah? That's what it means. Okay.
Is there any assumptions about the shape of GD? Is it rotation symmetric at all, is it?
There are no particular, I mean, as long as it fulfills this condition, that's the only thing, yeah? You could have even triangles, I mean, there are different shapes that you could use.
But in each dimension it can be different?
As long as it has this property, yes. Yes, it could be different, yeah. Okay. Right, so, okay, as I said before, this is the smoothing kernel, also known as the moving average function. And then this model was introduced in NIPS in 2005. The dependent Gaussian process assumes a particular form from this underlying function, and that form is just a white Gaussian noise. Yeah? So this is basically what is going on. We have the Gaussian noise, and then what I'm doing is just smoothing that noise using these smoothing kernels, and then what I get is the representation for the outputs, which is, looks quite nice. Yeah? All right. So let us compute the covariance or the cross covariance between two processes that are represented using that integral that we saw before. So I use the definition for the covariance. So this is the expected value of fdx and times fd prime x prime. So the first term here is fdx, and the second term is fd prime x prime, minus the expected value of the first term times the expected value of the second term. Yeah. So what is random in this function, this integral? What is random is the Leighton process, yeah, because g is just a given function. So I can put the expected value inside those integrals, and I get these expressions that you see here. Yeah. So the expected value acting over u only, and also for these other terms acting over u. And then I can factorize the integrals, and I get this expression that you see here. Yeah? Right, so what is this by definition? Sorry, say again?
Kernel.
It's the kernel, yeah? It's the covariance function of u. Yeah? That's it. So I get this general expression to build the covariance function, or the cross covariance between two processes D and D prime. Is that correct? Do you understand that? Right, so what covariance should I choose for K? Well, as I said before, this dependent Gaussian process model assumes that the Leighton process is random noise. Yeah. So what would be the covariance for K? If the Leighton process is noise, white Gaussian noise, what would be the expression for K? Say again? Right, yeah, the Dirac delta. So the Dirac delta, like this, and then we have like a power of this process of just the That's the coefficient sigma square. So if I plug this into this expression, I get this new way to build covariance functions that is just going to, so I basically go rid of one of the integrals, yeah? And I got just this, this one integral between the two smoothing kernels. So look at the integral contains x and x prime, and the variable z is the one I'm using to integrate. Yeah? Okay. So how do we use this in practice? Well, we need to assume some form for the smoothing kernel. And the form that we assume, as I said before, is such that if I integrate the square of that smoothing kernel, that has to be finite. So one easy choice is to assume that those smoothing kernels have the shape of sort of like a Gaussian form, like the one that you see here. Yeah? So I'm assuming that the smoothing kernel has this Gaussian form, where I have this parameter PD. It's not really a distribution. In a distribution, we would say this is a precision matrix. And then what I have to do is to plug this expression in there to find out how to compute the cross covariance between FD and FD prime. Luckily, these are Gaussians, and I'm integrating over the whole space. Then I could use the identity of the product of two Gaussians. And if this is one Gaussian and this is the other, then this is the result that we get. And then plug this result inside and solve for the integral. This is the result that we get. So as a little exercise for you, 5 minutes, 10 minutes, please get to this expression by using the identity of the product of two Gaussians. Can you work on that, please?
That's what we're trying to get to. What are we heading towards? Is that?
Second, sorry?
What are we heading towards?
So you have to get to this expression, yeah? Starting from this one. Yeah? Is it clear what you have to do?
Yeah.
It's just 2 lines. Just I want to see you working a bit.
Is it like an RBF kernel?
Looks like, yeah. Looks like. More like ARD kernel. Yeah? Because you can allow that matrix PD to have different length scales. Yeah. Yes, because they are just, once they copy, I can move the slide, yeah. So if we took all this expression here and leave aside the SD, that has the form of a Gaussian, yeah? With precision matrix PD. So we can express the GD x minus C as SD and a Gaussian, yeah? And then I could say X and then treat C as the mean, and then PD, which is the precision, yeah. I could write it the other way around too. I could say given X. That's the nice thing about that quadratic form, yeah. So this is GD, and GD prime X prime minus Z, which is the other one that we need, will be just the same one, but replacing X for X prime and D for D prime, yes? So it will be S D prime and of yep. What do we do now? Oh, we take those expressions and put them inside the integral, yeah? So we say the covariance fd x fd prime x prime is sigma square, the integral of a Gaussian of z given x pd z given x prime pd prime minus 1, and I'm integrating over z. Yeah? And then I just apply the identity. So I need to replace this multiplication of Gaussians that I have on this side for this one. Yeah? So what do we get? Sigma square, the integral. What will be the first term? Which one is the first Gaussian? So this Gaussian here. So I have to take the first mean of the first Gaussian, the second mean of the second Gaussian, yeah? And then add the covariances. Yes? So I get the Gaussian, the first mean is x, yes, given the second mean x prime, and then I add the covariances. And how is the second Gaussian? So is the second Gaussian is going to be over x, in this case x is z, given a mean value mu c and a covariance PC, so precision matrix PC, and then the integral over z. If we look at the mean of mu c, so this mean is built in this way, as you see here. So mu1 is x and mu2 is x prime. Yeah? What can we observe? What do we do observe here? So from these two Gaussians, the only Gaussian that I really care about is this one, yeah? Because the variable will appear there, and then I need to make the integral over z. So this Gaussian, I can move it outside of the integral. Yeah, so I get square and then the Gaussian of x in x prime, the minus 1, d prime. And then I have the integral of this other Gaussian over z with mu c, c minus 1. What is the value of this Gaussian, of this integral, sorry? 1. Right? 1. It's the property, yeah, of a density function. And then I get the result, which is the covariance for the cross covariance between FD and FD prime. Yeah? So that's the result. We have that in the other slide. I just call this P equivalent, I think, in the other slide. Okay, good. This is the expression that we get, replacing the Gaussian for the exponential. Yeah. Okay. Any question? Okay, let's move on. I can use these expressions, again, to build my covariance matrix and then sample from these processes. These are two samples that I get from this process convolution where the Leighton process is Y Gaussian noise. This is another sample. And then again, if I have observed data, then I have some input locations that define the random variables of the process, and I can jointly model them using a joint multivariate Gaussian distribution, as you see here. And then the elements on this, the elements of this covariance matrix can be computed, for example, using this expression for the covariance. Yeah? So I would need to know what is PD and what is PD prime. Well, for D equals 1 to D, capital D. I would need to know what is the value of sigma square. Yeah? But these are problems of, say, model selection, and we'll talk about that later. Right. Okay. We can go beyond Y Gaussian noise. So before we said that the Leighton process was a Y Gaussian noise, it doesn't have to be like that. It could be whatever Gaussian process with a generic covariance function. And in that case, I again obtain this form for the cross covariance, but now I can't just reduce this to one integral. So I would need to make two integrals. And then the easiest example of this type of process is, again, if I choose form of the Gaussian, sort of Gaussian form for the smoothing kernel and Gaussian form for the covariance of the Leighton process. And then again, applying the same tricks that we saw there, we can compute the covariance or the cross covariance, which is going to have this form that you see here. But now the covariance, the equivalent covariance or precision matrix includes this additional covariance that was the covariance of the Leighton process. Yeah? All right. Any question? Okay, good. Very good. So, probably this is the more complex model that we have talked so far. And it turns out that all these other models that we saw before can be seen as particular cases of this one. So I can generate a very complex one, or the most complete model, saying that this is going to be the double sum that we had in the linear model of regionalization. But just instead of just scaling the Leighton process, I'm going to smooth the Leighton process. So I'm just going to change that multiplication for the convolution integral. Yeah? And then I can work out the covariance of this representation for the outputs, and that covariance has this form. So we have two sums, as before, but we have two integrals that come from the convolution operation. Right, so this covariance function is probably the most general model if we want to build cross-covariance functions for the outputs. And again, all the models that we saw before are just particular cases of this form. So, for example, the intrinsic co-regionalization model and the multitask Gaussian process. How can we get the intrinsic co-regionalization model from this expression that you see here? So for the intrinsic co-regionalization model, we would say capital Q is equal to 1. Very good. It's equal to 1. Yeah. And if I want to get rid of this convolution, then what I say is that the smoothing kernels is just a Dirac function. And then if I plug this Dirac function here, then I just get with the constant the same here, and then I get the expression for the ICM model. This is the expression for the ICM model. Yeah? So it's a particular case of this integral, so this double sum and integral on the top. Then this is the expression that we saw before, the Kronecker product for the covariance matrix, and these are some samples. So this is the case where we have rank 1. This is the case where we have rank 2. The solid lines are one sample for the two outputs, F1 and F2, and the dashed line are another sample for F1 and F2. As you see for the rank 1 model, what we observe is that the two outputs are pretty much the same. So if we compare the two solid lines, they have basically the same shape. If we compare the two dashed lines, they have basically the same shape. The difference probably is in the scale. This is rank 2, so by adding additional process, we just break this symmetry between the two outputs, and we get somewhat more different samples. Again, this is the general expression. How do we get this semi-parametric Leighton factor model? What would be the value of R sub Q? 1, yeah, 1. And then again, we replace these smoothing kernels just for Dirac deltas. So we do that. We get this expression, which is the expression for the semi-parametric Leighton factor model. And again, I can write this in a matrix form, as you see here. So remember, this semi-parametric is just the sum of Kronecker products between these outer products and kernel matrices computed from the covariance functions of these Leighton processes. And these are two samples that I get from this process. So in this case, the solid line again is one of the samples for F1 and F2. And the dashed line is another sample for F1 and F2. Right, so the linear model co-regionalization is just make these smoothing kernels equal to Dirac deltas. And then I get this double sum that we had before. This is the matrix version. And then this, again, two samples from the process. Here again, I'm trying to combine Leighton processes that have longer length scale and shorter length scale. And the last case that we saw is the dependent Gaussian process, where we assume that the capital Q is equal to 1, RQ is equal to 1, and the covariance function is just the Dirac because it corresponds to a white Gaussian noise. And we get this integral that we saw before. We computed that covariance over there using a particular form for GD. And here is a comparison of the different models. So in this column, we have ICM. In this column, we have linear model co-regionalization. And in this model, we have the process convolution. So if I were to ask you, what of these models, or which of these models gives you more flexibility, what would be your thoughts about that?
I would say PC is the more general case.
Okay.
But my concern is by looking at all this math and stuff, you end up having things like Gaussians, right, when you do the convolution. And so everything's a squared exponential at the end of the day. And so the question is, you know, like whether it really is that powerful. That's my thing.
Okay. Okay. You can solve the convolution not only for Gaussians. Yeah.
I know, but like, what are like? I guess I don't have enough experience to know like what is on the other side, basically. What kinds of functions would you be able to get? Right.
So one type of functions that people use a lot, and we have worked on that, is when these smoothing kernels can be are basically the impulse response of a dynamic system. So you can transform differential equations into smoothing kernels. Yeah, and that's like a big area if you want to work with partial differential equations or ordinary differential equations. Yeah, that's one thing. However, even this simple model has more flexibility. And the reason is as follows. This is an extreme case. I have two outputs, but one of the outputs has, if you want, a longer length scale than the other one. I can control for that length scale by manipulating the smoothing kernel in the process convolution. But to get this effect using one of these models is not as easy as that, because in the linear model regionalization, the effect of the Leighton functions is the same over all the outputs. Yeah, because you're basically making linear combination of those Leighton processes. In the process convolution, you are modulating for each output the effect of the random process over the output. So imagine a problem where you don't have two outputs. Imagine a problem where you have millions of outputs, thousands of outputs. Yeah? So probably in that case, it's easier, and well, experimentally we have shown that, to get better results if you can modulate these smoothing kernels that trying to find a proper combination of Leighton functions that allows you to explain the variability in those 1,000 outputs. Yeah? Okay. Right. So if you want to read more about this, there is a review paper, and you can look at more details and explanations there. Okay. How do we use this actually for prediction? Well, we already saw that, okay, we can compute the cross covariances, and okay, there are different ways in you can do that. What can we do with that? Well, the good thing about this is that once you define a nice covariance function to compute your kernel matrix for the whole vector, then this is basically a Gaussian process. And all the tools and all the tricks that we saw yesterday for Gaussian processes apply here. Yeah? So again, we have a set of the outputs. Then we compute a valid covariance function for those outputs. And then if we have some isotopic data case in which all the outputs share the same inputs, then we can stack the random variables associated to F1, the ones associated to F2, etc., until Fd, and this is a large F vector. And then we have now ways to compute this big covariance matrix such that the blocks outside the diagonal are different from 0, so that we can exploit dependencies between the processes. So we have that, and then we could have, as the question you had before, add noise to each of the outputs. Yeah? So if we have noisy observations, we could have a process. If we want to do regression, let's say under a Gaussian likelihood, we can add some noise to each of the Leighton processes to represent the output. And then this is the likelihood that I get. Again, it's a Gaussian, but now I have this matrix sigma that encodes the covariances of these noise processes if you want. Yes? Right, now we have the same problem, and somebody asked before, how do we choose those parameters? Yeah? How do we choose the co-regionalization matrices, or how do you choose the parameters of these smoothing kernels? Well, we could just treat that as hyperparameters. I use some optimization procedure, or use some inference procedure, sorry, to estimate those parameters. Yeah. So the easiest one that we use commonly in machine learning is type 2 maximum likelihood, or empirical base. So just to maximize the log marginal likelihood. Yep. So we estimate the hyperparameters by maximizing the logarithm or the marginal likelihood. Okay? Right. Any question? Yes?
Is the covariance matrix not bigger than the single output?
Yes.
So how do you invest that?
Well, it's a very good question. I'm going to refer to that later. Yeah? Yeah. So basically, you have to use some sort of computationally efficient method, and people have worked on that already. Okay, so then if you want to make a prediction, then again, let's say you have a matrix X star of inputs, and you want to make predictions there, then you can just use the fact that this is Gaussian, and then you condition and find the predicted distribution. And this is the form of the predicted distribution. We have this mean, which follows this form here. And we have this covariance, which follows this form here. Yeah? So those are the same equations that you saw yesterday for prediction with single outputs. The only thing different here is that you have to remember now that this is a huge covariance matrix that has to be computed using one of these valid forms of computing cross-covariance functions. Yeah? Okay, so when we were talking about the ICM model, I mentioned that if you want to do prediction and you're working with noise-free data under the isotopic case, the prediction that you make using the ICM is equivalent to do independent prediction over each output. Yeah? You remember that? I said this is a phenomenon known as autocorrigibility, and we're going to see that again when we talk about prediction. Well, we're talking about prediction. And what we want to see is why that happens. So this is the mean function for prediction. Yes? And what we want to do is how this equation turns into independent prediction when I work with the noise-free case. Yeah? So let's do it here. And let's assume that we only have two outputs. So my vector f is going to be a vector f1 for the output 1 and f2 for the output 2. Yes? And what I'm saying is I want to make predictions on test inputs x star. I'm going to see how the mean looks like if I work with noise-free observations. If I work with noise-free observations, then mu star is going to be k f star f, and then what is inside the inverse? So it's just going to be KFF inverse because the observations are noise-free, conditioning on some vectors F. But F is F1 and F2, right? Good so far? Okay. If we are working with the ICM model, what is the form of this covariance matrix? So KFF is equal to, can you remember? Can you look in your notes? No notes. What is the form of that covariance matrix for the ICM model? Second? B? Correct. That's the, but very good. But for the covariance matrix, not the covariance function of the vector. So in the terms of the covariance matrix, it could be the Kronecker product, very good, Kronecker product between B and the kernel that we use for that underlying process. Yeah? Right, so let's plug this inside here. And then for F star F, what this means is a covariance matrix between the test points, yeah, and the training points, let's say, yeah, on your data. So I'm just going to refer to that because this has the same shape than this, but instead of K on the training data, it's going to be K between the test inputs and the training data. So I could just replace this expression by V Kronecker product of K. I'm just going to call it a star. Yes? And then inside the inverse, just plug this Kronecker product with K and then F. Are you familiar with properties of the Kronecker product? So what is the inverse of the Kronecker product? Very good. So we have Kronecker star, and then we have Kronecker F. Right? how do I multiply these two Kronecker products? So if these matrices have the same dimensions, or the correct dimensions, I can just multiply this term times this term, so I get B minus 1. Kronecker product with K star K minus 1 times F. Yep. This is the identity. So we get the identity Kronecker product of K star K times F, which is a vector of F1 and F2. How is the Kronecker product between I and this term?
Matrix where you have that matrix block diagonal twice.
So it will have K star K. What will be the term here? 0. What will be the term here? 0. And then the same here. Times F1, F2. What does it mean? If you want to make predictions, let's call it F star, and I make this multiplication, then I get F1 and F2. Is that right? So the prediction that I'm doing is an independent prediction, because you are using F1 only to predict the test cases for F1, and F2 only to predict the test cases for F2. And this happened because of the phenomenon of autocorrigibility. You see? If we have had the noise here, then I can't apply this property here. Yeah? And then I would be forced to use both outputs to make predictions for both outputs. Yep. Okay. Right.
Sorry.
Yep.
Is there some intuition behind that? That like if there is noise in the data, then the two Gaussian processes they have to be correlated, or their predictions?
Say again, sorry?
Is there some intuition like that I'm missing, that if there is noisy data, then it is obvious that the two processes have to like be correlated somehow?
Yeah, because I guess there is no way in which you can separate the contributions of F1 and F2. Yeah,
okay.
because the noise confuses everything.
Okay.
Yeah. Okay. Right. So this was an exercise for you. We did it. I'm just going to mention Krokriegin and then quickly go through the extensions and finish. So Krokriegin is the term that people usually use in geostatistics to refer to Gaussian process prediction as we understand it in machine learning. Yeah. So the difference between the things that we do usually in probabilistic machine learning and let's say this area of Krokriegin that comes from classical statistics is that usually in machine learning we separate the process of modeling the uncertainty and the process of making decisions. You know, probably this, yeah? So the first thing that we do in machine learning is to model the uncertainty, and then we use sort of generative models, probabilistic models to do that for the particular application that we have. And once we model the uncertainty, we use that uncertainty and we use decision theory to make decisions. So we combine that modeling of the uncertainty with a loss function, let's say, and then we take decisions. That's the way we usually work in machine learning with probabilistic models. So my question for you is, if you're doing Gaussian process, and then you have to report in your paper your result or whatever, then usually you're going to use the mean function of the prediction of the Gaussian process. Why do you use the mean function? Have you ever wondered that? What is the assumption behind just using the mean function?
Because it's minimizing the square error.
Very good, yeah. Because you are imposing a loss function that corresponds to the square error, and under that loss function, the optimal prediction is given by the mean. But that doesn't happen all the time. It's only under that loss function. Yeah? In frequency statistics, usually you don't start that way. You start saying, what would be the best predictor that minimizes my loss function? Yeah? So they talk about, probably you're familiar with it. I mean, some people here are from statistics. Unbiased, and minimal variance estimators. Yeah, so the idea here in co-kriging is that I build my Gaussian process estimator so that the prediction that I make is unbiased and has minimal variance. That's the idea in co-kriging. So it's sort of the same thing, but we start from the machine learning point of view, from the decision point of view, and then we build our model based on the decision. Yes? So if you go and look into a book of geostatistics, you're going to get a bit confused because this is a different way to do things. And then you see all these equations that are not very nice, a lot of symbols. But the idea is this, so you start very quickly. So you start with this, this is your estimator at a test input, yeah? And then what I say is that I can estimate that if I make a linear combination of the data that I have. So my question is, how do I find those terms, these are the weights, so that my prediction is the best prediction? So what do you mean by best prediction? So in the terms of classical statistics, it would say, well, a best predictor is if your predictor is unbiased, so this term is unbiased, so almost all the time that you get it, you're going to get the correct mean, and it has minimal variance. Yeah? So almost all the time that you make the prediction, the variance of the prediction is small. So this is what I have to optimize. And then what we do is that we find these weights so that this variance is the lowest. Well, it turns out, and it shouldn't be very strange, that the weights that optimize those values, this lambda here, is just given by this multiplication that you see here. Yeah? So basically, starting from the optimal decision, we are able to get basically the same equation for prediction in the classical setting of co-kriging. Yeah? We can talk about that during the day. Finally, I just want to talk about some extensions of this framework. We're talking about computational complexity. There are ways in which you can work, approach this. Now the matrix is scaling with D cube and N cube. Tomorrow, Richard Turner is going to talk about sparse Gaussian processes. So we can replace those matrices for low rank factorizations just by saying we don't work. So in the case of the convolution, for example, we are not going to work with the whole process U. We are just going to work with a process that is conditioned to some points of the process. Yeah. So those points of the process we usually refer to as random variables, inducing variables, is U. And then why this is sensible to do? Because if your, say your underlying process is sufficiently smooth, you only need to know some points of that process to find out what is the shape of the whole process. Yeah? And then this leads to also sort of low rank approximations. There is this paper where you can look at those approximations. Variations of the linear model of co-regionalization. This is the general expression that we have for the linear model of co-regionalization, and we assumed before that the Leighton processes were independent. So one version would be to say, well, let's assume that those random processes are non-orthogonal, and then you came up with these co-regionalization matrices when these two processes have some sort of correlation, and we call those the cross-co-regionalization matrices. This is a model that appeared in Statistics in 2002. You can make non-stationary versions of the linear model co-regionalization. So this would be a way to write the semi-parametric Leighton factor model. So where I'm transforming the Leighton vector Ux to the observed vector, a random vector Fx. And instead of making this A fixed, I make that A changes with the input location. And this model that used this form was proposed by Gelfand in 2004, but then it was reintroduced to machine learning, and I think I started ICML in 2012 with the name of the Gaussian Process Regression Network. Right, variations of process convolutions. There are several variations. We can make a discretized version of this integral. It makes it easier to get rid of these covariances where you have to solve these double integrals. You can do non-stationary versions, either by assuming that the parameters of the smoothing kernel changes with the input location, or the Leighton process is non-stationary. And you can also do dynamical systems, as we were talking before. We can do ordinary differential equations. For example, this is a first-order differential equation, or the smoothing kernel associated to that equation. This is the smoothing kernel associated to a second-order differential equation, and this is one for a partial differential equation. Right. Okay, just to finish, we have seen that we could do multitask learning or transfer learning using Gaussian processes. I think that's the takeaway message. Different ways to build meaningful cross-covariance functions, linear model Regionalization family or process convolution family. Once you have defined this form of constructing your covariance, then you can do all the things that you know how to do with Gaussian processes, with single output Gaussian processes. Kriging is just prediction with GPs with a quadratic loss function. We saw extensions of the linear model Regionalization and process convolutions. And this current research, people still work on this. Obviously, how to define cross-covariance function. There's just a recent newspaper that is going to appear in December, where they work with the spectral representations of these process convolutions. Okay. Yep.
When you were talking about the optimization, you treat like the coefficients in the B matrix or the parameters for the smoothing function as hyperparameters. But do you sample from the Leighton Gaussian process each iteration, or you just sample it to get those like additional functions at the beginning and then you don't change them?
No, you don't have to sample. No. You just treat the.
You're doing expected value.
Yeah.
So you are mostly talking about the isotopic data.
Yeah.
Heterotopic data, you have no rows and columns where you don't have the information.
No, you can just, so what happens in that case is that the K that we had before, so we wouldn't be able to write this as a Kronecker product anymore. We will need to write the actual element by element, and then each matrix is going to have different size. Yeah, according to the data that you have. Yeah. Okay, no more questions? Right, so I think there is coffee now, and thank you.